Hello! This video is for Module 3, Part 1, and includes a discussion of classification. In particular, we will be considering a logistic model in this module. Okay, let's go ahead and get started then. So, a classification problem is when the response variable is not numeric. So up to this point, in all of our examples and modules that we have considered, the response variable has been numeric. Here, the response variable is going to be binary. So for example, if I wanted to predict the probability of somebody surviving a stroke, so my outcomes there are either yes or no, then the response variable is categorical and is said to be binary. In this situation, this class of problems is called a classification problem. One of the simplest models that we can use for a classification problem is a logistic model. So we will talk about that here in this module. The example that we are going to use here is from the National Institute of Diabetes and Digestive and Kidney Diseases. And it is a data set on, is it Pima Indians? So it's called the Pima Indians Diabetes Data Set. This data set is widely available on the internet. I did notice that many of the observations had a BMI value of 0 or a systolic or diastolic blood pressure value of 0. So I removed some of those observations from the data set. There is a files folder that exists here for this module, and that is provided here. The Colab document will show you obviously all the code to produce the output that I'm presenting here. Here's what the data looks like. There are a few variables here, but we are going to just start with a simple model here. The variable that I want to predict for is way over here on the right, and that is whether or not this person has type 2 diabetes. These are all women here in this data set. And the predictor variable that I'm going to consider is just age. In the next module, we will consider some of these other variables that are present in the data set. So the goal is to create a predictive model so that I can get the best prediction possible for type 2 diabetes. Okay, so let's just talk about logistic models from a kind of higher up perspective before we get into the details of the output. I've just created a set of plots here that'll help guide us through the discussion of what a logistic model is all about. So here I have just a set of observations. I have the age here, and then I just have whether or not they have type 2 diabetes. A plot of this data would look something like I have here on the left, where the y-axis is just type 2 diabetes no is on the bottom here and yes on the top. And then across the x-axis is just the different ages. So you can see I have 21, 23, 25, 27, and 29. Looks like there's 5 observations there that do not have diabetes. They're plotted here. And then those that do have diabetes are ages 68, 69, 78, etc., and they're plotted here. Here's a second plot, which is much like the first, except that the observations for yes are spread out a little bit more compared to the no's. In both of these plots, it's going to be fairly easy and straightforward to make a prediction for whether or not somebody has diabetes. If they're in region A, I'm pretty sure or pretty confident that those individuals do not have diabetes. Okay, and I'm going to be equally confident that the individuals in region B do have diabetes. So let's suppose that I get another woman that shows up and her age is 24 years old. She's probably not going to have diabetes based on this data. Likewise, with the second set of data that I have here, there's still a right? Region A here is different than region B in that anybody that's less than about 45 years old is not going to have diabetes, and anybody that's at about 50 or higher, I'm going to classify them as having diabetes. So I either classify an individual as not having diabetes or having diabetes. The age here does a good job of discriminating between these two groups, right? So if I'm less than 45, I'm going to say no, they don't. And if I'm greater than 45, I'm going to say yes, they probably do have diabetes. So again, what we say here is age does a good job of discriminating those two classes. Likewise up here. Now, in reality, it's never this clear cut. So I have a couple of other examples here. So here I have a set of people that do not have diabetes. It looks like their ages go from about 20 up to about 60. And then I have another set of individuals or women here that do have diabetes, and their age group, range is from about 45 up to 80. In region A here, I'm pretty confident that they do not have diabetes. So a woman that's 35 and less probably does not have diabetes. Somebody that's 70 and above probably does have diabetes. I saw 2 women in that group, and both of them have diabetes. Predictions get much harder here in region B. You can see that I have some women between the ages of 40 and 60 that do have diabetes, and then I have others that do not. So my ability to make accurate predictions here in region B is going to be hindered a little bit because I have both people with diabetes and others without in this same age group. A logistic model actually constructs the blue curve that you see here in plot 4. What is on the y-axis in plot 4 is the probability, okay, that they're going to have type 2 diabetes given a woman's age, given age. So what do I mean by given age there? For younger women, so let's suppose that their age is 35 years or less, that's going to be region A here. The chance that they have type 2 diabetes is pretty small. It looks like my model is saying that's about between 20 and 30% here. So the y-axis here is the predicted probability of having diabetes. On the other hand, in region C, the predicted probability that they have diabetes is going to be quite high. Okay, again, I only saw 2 women in that group there, and it's quite high. And both of those women, had diabetes. So that predicted probability for region C is going to be way up here, around maybe 80 or 90%. In region B, the predicted probabilities are going to be closer to a 50-50 case. It's harder for me to discriminate which class they belong to when their ages are between 40 and 60. My logistic function, okay, that's what this blue line is kind of in the middle there for those predicted probabilities when I'm between the ages of 40 and 60. How do we make predictions using this logistic curve? Well, if I'm more likely to end up having diabetes than not, so when the predicted probability gets at that 50% threshold or higher, I'm going to predict them as having diabetes. When the predicted probability, again the blue line here, is less than 50%, then I'm going to predict them not to have diabetes. So there's 2 steps that we need to use when we're doing logistic modeling. The first is to get this blue curve, which is just the predicted probabilities of having diabetes. And then the second thing is to actually classify them into either no, they do not have diabetes, or yes, they do have diabetes. Okay, I think we covered most of those discussion points. You can read through those if you would like. Here, what I've done is just showed you that you don't have to model the chance of somebody getting diabetes. We could determine the probability of somebody not getting diabetes. Now this is very much the same, it's just that I'm going to put the no group here on the top and the yes group on the bottom. And my predicted probabilities are going to decrease as I increase age now. So again, what the y-axis here is, what is the chance that they do not have diabetes? Well, that chance is going to decrease as somebody gets older. So this is just kind of the opposite of the curves that we had up here. Now, when we are modeling or doing logistic modeling in our computing technologies, we have to identify, or we have to be careful to understand what is the model actually predicting. The chance of getting diabetes, which is this plot, or is it predicting the chance of not getting diabetes? So that needs to be specified in our computing technologies so that we know what is actually being modeled. All right, these last couple of plots are just showing you some other logistic curves. So curve A is what we have presented up above. Curve B here is just showing me that the predicted probabilities increase much more quickly for younger ages. And then after about, what is that, about 50 years old or so, then it kind of levels off. Okay, so if we had, what is the difference between curve A and curve B here, is that the predicted probabilities of getting diabetes are much higher for younger people under curve B than under curve A. In contrast, over here on the right, I have curve C versus A. Here, the predicted probabilities of getting diabetes is very stagnant. It's very doesn't increase very much. It's fairly consistent until I get to about 70 years old, and then it really takes off. Okay, so these logistic curves can have different forms here, and the data is used to determine what the form of that logistic curve looks like. Now here is the actual data. So I have on the y-axis again, no, they do not have diabetes, and then up at the top is yes, they do have diabetes. And you can see that it's going to be much harder for the actual data to discriminate between not having diabetes and having diabetes. Okay, we will see our logistic model here is not a great logistic model, and that is because age does not do a real good job of discriminating between these two situations. Okay, let's talk about the implementation of logistic models in our computing technologies. Some computing technologies require that my response variable actually is numeric. Okay, so the algorithms that are used to fit these models, okay, are very, they require numeric outcomes. A computer is not going to know what to do with a yes or no response. Okay, it has to work with numbers when it's trying to fit these models. So the standard thing that we normally do here, or the standard numeric representation for a binary response, is to give the value 1, okay, for the outcome that you are modeling. So here I want to model the chance of a type 2 diabetes, so that is going to be indicated with a 1, and then a 0 is going to be that they do not have diabetes. Another thing that you need to concern yourself with when you're fitting these models is, what is the computer considering the success to be? Okay, and success here is in quotes because it's not a good thing if a woman has diabetes, but that's what I'm modeling. So here in this module, a success is going to be a woman having diabetes. The following is an example of a simple logistic model. It is simple because I am only considering one predictor variable here, and that is age. The left-hand side of this equation is more messy. It is not just the response, nor is it the numeric representation of the response, but what it is a function of the predicted probabilities of having diabetes. So in this equation, theta represents the chance or the probability of somebody having type 2 diabetes. This function here is called a logistic function. And what that does is it ensures that the responses that I get back are between 0 and 1. This is a probability here. The y-axis is a probability, and all probabilities need to be between 0 and 1. So that logistic function ensures that this logistic curve will stay between 0 and 1. Irregardless of the shape, it's going to stay between 0 and 1, and it has to, because again, I'm predicting probabilities, and all probabilities need to be between 0 and 1. So this is a special type of function that does that for me. A logistic model is a type of what's called a generalized linear model. And this is beyond the scope of this course. We're not going to talk about generalized linear models in this course. But the one thing that I do need to specify when I'm fitting this model is what type of distribution is the response. Now, the response that I'm considering here is binary. It's categorical. It has 2 levels. Yes, they have diabetes, or no, they don't. And the correct reference distribution for that response is a binomial distribution function. So when I'm fitting this in my software, I'm going to have to specify that function, or excuse me, specify that distribution. As I said, there's 2 steps of getting the predictions. The first is to manipulate this equation here. Actually, I just need to solve this equation for the probability of having type 2 diabetes. Okay, right? That's what this is on the y-axis here. So I need to be able to, that's going to be my response, or my y. So when I do that, here it is, that's my y now. And then what's going into these predictions is the age here. So again, this function right here is going to ensure that my probabilities stay between 0 and 1. Now, once I have that logistic curve, which is this thing right here, I just need to decide what am I going to classify as those having diabetes or not. And oftentimes we use that 50% threshold. So up here, when I was talking about that, anything that's when I'm more likely to have diabetes than not, then I'm going to predict them to be yes. So any woman that is, it looks like about 45 or higher, is going to be predicted to be yes. Any woman that is of age 45 or less is going to be predicted to be no. So there's a lot of work going into that model, but it really comes down to where does this curve cross this threshold? And if I'm above that, I'm going to predict them to have diabetes, and if I'm below that, I'm going to predict them not to have diabetes. That's the idea of a threshold. Okay, so the Colab document here discusses or shows you how the model is fit. I'm not going to go into too much detail here. The estimate here, okay, those quantities there are used to get my prediction equations. Just make note that I am indeed using family binomial there, and again, that's appropriate when my response is binary. I take these estimates, I plug those into my prediction equation here. I got to do a little bit of math to solve for those predicted probabilities. And this right here, this negative 2.68 plus 0.06 times age, is this function right here. 1 all over 1 plus e, right? So all that kind of garbage in there gives me this nice logistic curve. As I've already talked about, once I'm exceed a particular threshold, I'm going to predict them to be have diabetes, and over here I'm going to predict them not to have diabetes. We're going to talk quite a bit here later in this module about what is my threshold value. Here I'm just leaving it at 50%, but we're going to talk more about that down below. Okay, now we're ready to talk about the performance metrics for these predictions. The first thing that is created is what is called a confusion matrix or confusion table. So let's take a minute and just understand what is being presented in this table. The rows of this table are the actual outcomes, and the columns in this table are the predicted outcomes. So, how many total people are in my analysis here? I can just add up the 293, 31, 121, and 45. If I take the 293 and the 31 and add them up, I'm going to end up with 324. So the total of these two is 324. Now what does that tell me? If I sum these two up, then these are the total number of people in my data set that actually do not have diabetes, which is 324. If I sum up the 121 and the 45, again, sum those up, get a total over here, that's going to be 166. 166 people actually do have diabetes in my data set. So what would this 293 represent right here? Well, that is going to be people that actually do not have diabetes, and my model said or predicted that they do not have diabetes. So I did pretty good. There's a lot of people in this data set that do not have diabetes, and often the model actually predicted that they do not have diabetes. How about this cell over here? Down here in the lower right. Here I had 45 people, okay, that actually had diabetes, and my model predicted them to have diabetes. That's doing okay. However, let's look at this cell. This is, my model said they do not have diabetes, but they actually do have diabetes. So those are mistakes. And there's a lot of them here. 121 women. Okay, for 121 women out of the 490 in my data set, my model said they did not have diabetes, but they actually did. 31 here is another mistake. And these are women where they did not have diabetes, but I said that they did, or the model said that they did. Okay, so let's go back up here and just look at the data a minute, as long as I had that plot. What were these two numbers again? 31 and 121. Okay, let's go back up here a minute. What my model's going to end up doing after looking at the logistic curve is when I am at about 45 and above, I think it was, I was going to predict them to have diabetes. I have 31 down here in this lower group that are over the age of 45 that do not have diabetes. So all of these here are going to be mistakes in terms of my predictions. Remember, my logistic curve crossed at about 45 or so. I have 120 or 130 or whatever it was back here below 45 up in this group. So those are all mistakes that my model would have made. I certainly have more people that don't have diabetes that are at age 45 or less, but I do have a good number up here. So that's what these numbers, if you just kind of think about the graph that we have presented there, that's what these numbers are actually showing you, the 121 and the 31. I could visually show you that graph, right? Just kind of a stacked bar chart here. These are good. The 293 is good because that's where the actual was no. That's the darker gray there. And the left side is predicted no. So those 293 I got correct. The 45 are good because those are people that actually have diabetes and I predicted them to have diabetes, so that's good here. And then these are the off diagonals, what we call the off diagonals there. Those are my mistakes. Okay, let's talk about the performance metrics. First is accuracy, and that's very straightforward. It's the most simple method measure that we can have here for classification problems. And that is just measuring what proportion of the predictions did I get right. There were 293 no-no matches, and there were 45 yes-yes matches. 293 plus 45 is 338. There's 490 people in this study, so I have an accuracy measure of about 69%. The misclassification rate is often cited, and the misclassification rate is just the off diagonals. So there's 121 there, there's 31 there, there's 152 on the off diagonals, divided by 490, that's the 31%. The misclassification rate is just the opposite of the accuracy rate here. All the observations are either predicted correctly or predicted incorrectly. Now let's talk about one of the shortcomings with accuracy. So accuracy, as I said, is very straightforward, simple to understand, but there is a shortcoming to that. And that is, I suppose, or just suppose the predicted outcomes for every individual was just no. So I'm not going to do any modeling. I'm just going to say they don't have diabetes. Okay, no modeling at all. Just I'm going to say all people do not have diabetes. Well, I'm going to be correct, whatever 293 plus 31 is. That's how often I'm going to be correct. 324. 324 out of the 490 times, my prediction is going to be correct. I'm not doing any modeling. I'm not actually even looking at the data. Okay, I'm just blanketly saying nobody has diabetes, and I'm going to be right 66% of the time. Now, the accuracy from my model is only 69%, so I'm not gaining much. Okay. You might think initially, well, a model that had an accuracy of 69% is doing pretty good, but not really when you contrast that against somebody just saying, oh, nobody has diabetes. Okay, so that is a shortcoming in that measure. Okay. Another one that is cited by some computing technologies, and in particular R cites this one, is Cohen's Kappa. Cohen's Kappa involves, again, the situations in which the outcomes agree. That's that 69%. And then it contrasts that observed agreement by just chance agreement. Okay, so there's some calculations that are involved with that chance agreement. The Cohen's Kappa turns out to be about 0.20. This is a correlation type measure, so it's stuck between -1 and 1. The closer you are to 0, the less agreement you have. The closer you are to 1, the more agreement you have. So 0.2 here is pretty small. There are tables that are cited for Cohen's Kappa. Here is one that I just grabbed. If it's less than 20%, then they say that you have not much agreement or minimal agreement. Here I'm basically right at that none to minimal agreement. And if, again, as it gets closer to 1, you have nearly perfect agreement. Accuracy, again, is one that we use. Cohen's Kappa is used less. Area under the curve is used a lot for classification problems, so we'll spend a little time here with this one. The area under the curve is a metric that is used to look at the overall performance of a predictive model. It involves the following concepts: sensitivity, which is the proportion of people who have diabetes that were predicted to have diabetes. We want that thing to be high. Sometimes sensitivity is just referred to as the true positive rate. So of those that have diabetes, how many did I predict to have diabetes? That's sensitivity. Specificity, which is much harder for myself to say, is the proportion of people who do not have diabetes that were predicted to not have diabetes. So we want that to be high as well. The threshold value is used in constructing an ROC curve. And that is the 50% here is what we're going to use, at least initially. So we can compute sensitivity and specificity here with our data. So again, sensitivity is, what is it? The true positive rate. So let's look at the people that have diabetes. There's 121 and another 45 there. How many of those did I predict to have diabetes? Well, that's 45 divided by 121 plus 45. That's going to be about 27%. Now, to be honest, that's not very good. Of the people who have diabetes, how many did I correctly predict have diabetes? Only 27%. How about specificity? Specificity is going to look at this 293 out of the 293 plus 31. So this is, again, of those that do not have diabetes, how many am I going to predict to not have diabetes? That's the 293 divided by the 293 plus 31. That's about 90%. And that's a little bit better. Now, we want these things to be high, right? We want these, this is just the notion of making correct predictions when they do have diabetes and when they don't have diabetes. The following representation is often used here for sensitivity and specificity. So I already mentioned the true positive rate. That's that 27%. So sensitivity is just referred to as the true positive rate. Again, what proportion of the people that actually have diabetes did I predict them to have diabetes? And then we also have 1 minus the specificity. And what that represents is the false positive rate. Okay, so the false positive rates are going to be these right here. The 31 out of the 293 plus 31. That's going to be about 10%. So the false positive rate is of those that did not have diabetes, how many did I predict did have diabetes? And we want that thing to be low, right? We want 1 minus specificity to be low. Okay, there exists a trade-off between the true positive rate and the false positive rate. Again, for example, suppose one predicts that none of the women have diabetes. In this situation, the true negative rate is going to be 100%. So if I just say nobody has diabetes, okay, then I'm going to have a true negative rate of 100%. But the true positive rate is going to be 0. So I'm going to miss all of the people that do have diabetes. I'm just going to label them as not having diabetes. So that's bad. So there's a balance that has to exist between this idea of a true positive rate and a false positive rate. The choice of our threshold value definitely has an impact on the true positive rate or the false positive rate, or the sensitivity and specificity. The following is a receiver operating characteristic curve. So that's called an ROC curve. And what that does is it plots the sensitivity, which is the true positive rate, against 1 minus the specificity, which is a false positive rate. Now we want 1 minus specificity to be small, and we want sensitivity to be high. So what is the ROC curve actually doing here? What the ROC curve is doing is allowing me to, the ROC curve provides a measure, okay, which is the area under the curve. That's the measure here. And what that measure is actually doing is looking at the gain in using a logistic model compared to just a flipping of the coin. So if I just haphazardly flipped a coin to decide everybody's outcome, what I'm going to end up with is an area of 0.5 in that situation. And that diagonal line drawn on this plot is that random guessing. Now, I hope my model can do better than just randomly guessing, And it does. This ROC curve is puffed up a little bit compared to that diagonal line. So the area under my ROC curve from my logistic model is 0.723. Again, I'm gaining a little bit here relative to what I saw by just randomly guessing on the predictions. So this logistic model isn't great. Okay, we would like this ROC to be as high as possible. The smallest here is 0, or excuse me, the smallest is 0.5. That's a just guessing situation, and the largest would be 1. If this ROC curve is pushed way back up here in the upper left-hand corner, then that's going to be good. A little bit more about that. I want this curve to be as far to the left and up as possible, because on the y-axis here I have sensitivity, which is the true positive rate, and on the x-axis here I have the false positive rate, and I want that to be small. So I want to be up here in this corner, and the closest that I can do with this logistic model is right about here. This is going to, if I use the threshold that was used to obtain this specificity and this sensitivity, okay, I'm going to, in a sense, optimize my true positive rate and minimize my false positive rate. If I use this threshold, which we'll talk about that in a minute, then my sensitivity is going to be about 0.7 or so, and my false positive rate will be at about 30%. This is the threshold that I started with, right? 50%. And recall the sensitivity was at 27%, and my 1 minus specificity was at about 10%. I can do much better with a different threshold. I can increase my sensitivity up to about 70% if I move my threshold. So let's move our threshold down a little bit. We're going to move my threshold down to 40%. Look what's happening to these people that I'm predicting to have diabetes. Before, I only predicted 45 out of the 166 that had diabetes. I only predicted 45 of them to have diabetes. When I move my threshold down a little bit, I'm going to increase that to 74. So my sensitivity is going up here, okay, when I decreased my threshold from 50% down to 40%. If I decrease it even more, so let's move that threshold down to 30%, I can see that my sensitivity is now up to about 67%. So of those that had diabetes, I am now predicting them to have diabetes 111 times out of 166. However, I'm also predicting more. I am also increasing my false positive rate. My false positive, well, up here I only had 31 in that group where I made mistakes. Now I'm up to 106 mistakes. And again, the reason that's happening is because when I move my threshold down, okay, those that do not have diabetes are being predicted to have diabetes. So that's what I mean by that balance. We have to try to balance both of those. That sensitivity and also the 1 minus specificity. Obviously, if I move my threshold down to the bottom, I'm just going to predict everybody to have diabetes. My sensitivity is going to be at 100%. I'm going to predict all of them correctly. But my specificity is at 0. I don't predict anybody to not have diabetes. So this is really bad here. And I don't have any over here. I don't have any agreement over here. So that's your specificity. Again, we want both sensitivity and specificity to be high as possible. And this, I think right here, the threshold of about 0.3 does about as good as I can do with this model. Some final comments then. The process of building a predictive model for classification definitely has more nuances than a regression problem. So there's more things that we need to concern ourselves with. We introduced the idea of a generalized linear model. We have the idea of a distribution, a distribution for the response. The idea of just a single measure to best understand your predictions is not hold here for classification problems. Certainly accuracy is a good measure, but it's very simple. It's overly simplistic and should not be the only one that we consider when we're looking at doing logistic regressions. There is a concept of a residual or an error that exists for logistic models. However, this is not being covered in this module. The task here involves answering a couple 3 true-false questions, making sure you understand the logistic curve here a little bit, and then having you calculate some accuracy measures for this data that I have here. Okay, that does it then for this module. Thank you.